Hello everyone. Um, Today's session we focus on VLANs, VLAN principles and configuration. And for our introduction, we have Ethernet technology. I think we completed Ethernet switching just before this session, where we discussed the Ethernet technology being based on shared media and Uh, with that comes an issue collisions. Then we have more algorithms like the CSMACD in Ethernet, which helps uh, with the issue collisions. However, we might have other issues that might arise because of my shared mediums, while especially in a case where we have a huge number of a large number of PCs in that same sharing that same media. We have what we call broadcast storms, which will lead to a decrease in performance if we do have them. So my VLANs basically these are virtual networks, virtual local area networks, uh, where we segment our network at layer two. So it's basically segmentation at layer two. We did IP addressing. And when we did IP addressing, it's sort of the same concept. IP subnetting, I mean, not addressing. When we did subnetting, it's sort of the same concept. The difference being subnetting is dividing your network at layer three. Then we have VLANs being segmentation at layer two. So in a case where you have my routers, you can segment your network at layer three. Routers will facilitate that. At layer two, you can create my VLANs. They'll also be able to segment your network. And the goal is simple. Um, Security-wise, segmentation in my networks, security-wise, you're sorted. Performance-wise, you're sorted. Most of my changes are network in a certain network won't affect the other network because you've basically separated my networks. That's the overall goal, I think, of segmenting my networks in. So with VLANs, we're basically segmenting our network at layer number two. Objectives of the course: understand the background of VLAN tech, identify VLANs to which data belongs, master different assignment methods, describe how data communication is implemented, master basic VLAN configs. So basically, I think that's what we are going to touch here. Issues facing traditional Ethernet. Right, with traditional Ethernet, like highlighted before, one of the main issues is the repo come from having a shared medium. When we say we have a shared medium, it's like we are using uh, a motikari dzese dziri kushandisa one way. That's sort of an analog of having shared media. So if you're using one way for motikari dzese dziri kuenda in one direction and another, panoitika collisions, obviously. So with shared media, we have that issue yekuti every packet is fighting for the same media. Every device is fighting for that same media. So in a case where we have a broadcast, for example, there are what we call my broadcast storms which happen. So an example anokwanisa kupa of a broadcast storm ndeyekuti if we have a non-unicast frame. Let me see pen. Right, if we have an unknown unicast frame, when we did Ethernet switching, we said an unknown unicast frame is broadcasted a switch kana rasvika paswitch. Reason being, we don't know what the destination is. Right, if switch it broadcasts, then this switch will also broadcast, but probably device destination one device. But my broadcast, you can see my broadcast esasvika uko. My message esasvika. Anozosvika or reject on the other devices, but my messages anenge asvika. That is only from one device. That's a broadcast from one device. Now imagine a case where we have multiple devices also trying to broadcast. The problem yamunoita ndeyekuti performance of the network is affected because my devices ese they are processing my my packets or my frames which we can consider as junk traffic. It's not traffic invalid in the case of this slide. So processing junk traffic, it basically means processing power yese ruperera pane zvinhu zvisiri necessary. So that's the problem that we have with my shared mediums. The larger the broadcast domain is, the more serious network security and junk traffic problems are. So shared medium results in having a very large broadcast domain. I think we defined my broadcast domains, we defined my collision domains. Define a broadcast domain being a domain where if a device broadcasts, then every other device in the network receives the message. So with with the Ethernet technology, with the traditional Ethernet technology, with shared media, it basically means you have a huge broadcast domain. A huge broadcast domain is the problem. And my VLANs, they solve that problem. And how do they solve that problem? For that same switched network, Ethernet switched network, you create segmentation on the switches. All right. So for every, you might have a case where for every interface, it represents a virtual local area network. You could have every interface. For example, you could assign different VLANs on every interface. Assigning different VLANs on every interface basically means this interface belongs to a network number 10. Another interface belongs to a network number 20. So if you want to send a broadcast rinosendwa from a visual local area network number 10 will only be broadcasted to my interfaces which belong to VLAN 10. The same with VLAN 20. So broadcast here now is limited to a VLAN instead of the whole broadcast domain. The broadcast domain, from perspective, uh, yeah, the whole network, it might look like it is one, but nema VLANs tinenge taseparata tacreata ma virtual networks edu so that my broadcast domains edu they are then limited within those virtual local area networks. Characteristics of my VLANs: geographically independent. Only devices in the same VLAN can directly communicate at layer 2. So devices in the same VLAN, only devices in the same VLAN can communicate at layer 2. Devices from different VLANs can now communicate. We have what we call inter-VLAN routing. You then require routing. Can only two different networks and you want them to communicate. Routing is always the solution. So in this case, to separate my networks, tane VLAN 10 and VLAN 20, it means if these two wants to communicate, pakutoda router somewhere because they are two different networks. That's the idea behind having my VLANs. Implementation. All right, this is how it's implemented. In this case, implementation is using, we are assuming, is using interface-based VLANs. Right. So switch ready, we have switch ready, switch number 1, switch number 2. Without my VLANs, this is one broadcast domain. Erase. Suppose apana VLAN aripap. This is one broadcast domain. Meaning If this device broadcasts, then panapa pachafladwa something, kuno kuchafladwa, ichareceiver something. That is what a broadcast is. If we consider this as one broadcast domain, meaning at number VLANs, when we flood, then every other device in the network receives the message. With my VLANs, what we basically do is Tornado configured on this specific interface VLAN yedu VLAN 10. Let me see. Can I get this? All right. So with my VLANs now, tunaenda pa interface and we configure the interface and say frame richapfuura nepa interface apa riri VLAN 10, frame richapfuura nepa interface apa riri VLAN 20, the same here 20 and 10. What then that means is if this device broadcasts, traffic yedu will only go to this device. Why? Because it's in the same network, it's in the same broadcast domain. How? Via segmentation at layer 2. The same if traffic is broadcasted panap, inongoya on this device because that's the only device which is in the same VLAN. That's basically the idea around my VLANs in. Yeah, they're saying switch 1 and 2 belong to the networking enterprise. VLANs are planned. VLAN 10, VLAN 20. Employees in departments A and B are connected to the switch. Assume that a frame sent from PC1 reaches switch 2 through the link. If no processing is implemented, switch 2 can neither identify the VLAN to which the frame belongs nor determine the local VLAN to which the frame should be sent. Okay. Right. I've picked up another thing here. The reason why we have my VLANs, for example, you could have a company. This is one company. Instead of having one broadcast domain, putting every client, every device, let's say every device, every employee in that one broadcast domain, what you can do is you can separate my networks algo at layer 2. So you can say admin ESA, let them use VLAN 10. So every device which belongs to staff member admin, configure kuti it should be VLAN 10. So if I have another admin panel in a VLAN 10, I can say what else? Sales team. Today in VLAN 20. Another one in themselves twice and VLAN 20. You could have others with some VLAN 30, VLAN 30. What that means is tinogona tiri on the shared medium per switch ready. However, tinema virtual networks which we belong to which are separate. Traffic in VLAN 10 and 10, it belongs to the same network. In 30 and 30, it belongs to the same network. Can I send the traffic between different VLANs? Then I'll need to go via the router because ndakutoita remote connections basically. So the idea behind my VLANs is basically segmentation at layer number 2. How does a switch identify the VLAN to which a received frame belongs? Right, we have what we call my VLAN tags. My VLAN tags are basically what identifies kuti a frame belongs to what VLAN. So traffic yangu ikabva pa PC1 panapa ichisvika pa switch rangu on the interface inopiwa tag. Ndopa inopiwa tag kuti iwewe you belong to VLAN 10. So traffic painosvika kunoko, it is accepted. Why? Because switch inotarisa kuti tag rai VLAN 10 ere. Tag ikafanana ne-interface VLAN ID, then that's how traffic passes panapa. Tag iri traffic ikasvika panapa, tag iri inosiyana ne VLAN ID iri panapa. Dzikasiyana, that basically means traffic UI consequent on that specific VLAN. So my tags, they are very important. It's a way of identifying which VLAN does a specific traffic belong to. IEEE 802.1q defines a full byte VLAN tag for Ethernet frames, enabling switches to identify the VLANs to which received frame belongs. Okay, easy. A VLAN frame, its format, you see, tag read basically it's inserted in between the source mark and the length or a type fuse. I think this is an Ethernet frame. We took a look at that, I think, in previous sessions. Kuti frame rate or my fuse, I gotta say. I think this way the fuse angati now. So
What?
on a typical frame, you can mute. Where's that? Mshonga?
Oh, yes.
Mute. Right. So on a typical frame, let me put it this way. Let's say we have a switch, then we have a PC. Right. Traffic yedu painobva panapa pa PC apa. It is encapsulated ndo panobva frame rate. Frame rate rinobva rakadai so risina tag. Richibva pa PC apa. Ndo panobva Ethernet frame. Then parinosvika pa switch rinobva raederwa this field ish. This field iro ndo tag redo basically. Tag redo, it has the TPID, the PRI, the CFI, the VLAN ID. It is very important is this part here, VLAN ID. That is basically what identifies kuti VLAN yedu it belongs, kuti frame redu it belongs to what VLAN. The other fields, we have the tag protocol identifier, identifies the type of frame carrying. Okay, the TPID tag protocol identifier, it basically identifies the frame, the type of frame which is carrying our traffic. We have my Ethernet frames, Doma IEEE 802 point. Ethernet frames. Is it 3? 802.3. We have my Ethernet frames. We have my frames HDLC. We have my point-to-point, different type of frames that we have. So this field basically identifies kuti frame redu riri kutakura traffic yedu nderipi. Then we have the PRI, the priority, which basically identifies the priority of the frame. This has to do with quality of service, defining the quality of service priority of frame redu. The CFI indicates whether a MAC address is in the canonical format. For Ethernet frame, the value of the field is 0. The CFI is usually used, it goes hand in hand in quality of service, usually used to identify if a frame can be dropped kana tine congestion. It's a field report, run the CFI. Then the VLAN ID, like I said, I think this is a must know. VLAN ID it basically identifies with frame rate during VLAN IP. So this basically sums up with the tag yedu inenge inechi. That's the VLAN frame for you. VLAN implementation. The link between switch 1 and switch 2 carries multiple VLANs. 802.1q, often referred as .1q, defines a system of VLAN tagging for Ethernet frames by inserting a tag in the frame header to carry the VLAN information. Nothing much here, but I think it's very important looking at link between switch 1 and switch 2. We have type of my links at now. I think they'll be discussed in the slides, incoming slides. Link ERIR, which basically connects my switch edu. We call this a trunk. A trunk carries multiple VLANs. So traffic from VLAN 10 kana chida kuenda to this switch 2 inofurana apa. Traffic from VLAN 20 kana chida kuenda this side inofurana apa. So basically this link carries multiple VLANs and it's called a trunk. We have this link iri apa iri. It's called an access link. Link iri, it only carries traffic from one VLAN. So apa traffic atichaona ndeye VLAN 10 and only traffic ye VLAN 10. VLAN implementation example, ndoda send information from PC1 to PC3. What happens? Encapsulation per PC1, traffic yangu kana iri apa inenge iri untagged. No tag. Tag rinozouya painosvika panapa painterface iri ndo painobva yapiwa tag yam VLAN 10. Then yobva yaenda via trunk yedu yobva yasvika on this interface panoitwa de-encapsulation tobva taona kuti VLAN tag yedu is VLAN 10. Tobva tacompare neVLAN yeinterface yedu tobva taona kuti 10 as well. Traffic yedu yobva yakuVLAN 10. That's basically how my VLANs work. Very important understanding the working principle here, because when questions come, that's one of the few things that will be tested. Understanding kuti traffic kana uchitenda nema VLANs, what's the process? How does everything work kana tichishandisa VLANs edu? Assignment methods, we have different ways of assigning VLANs. The one yatiri kudiscuss from the beginning is interface-based assignment. That's the most common way of assigning VLANs edu. So for every interface, you assign that interface a VLAN. In this example, the concept interface E, VLAN 10, interface E, VLAN 20, interface E, VLAN 30. That is what interface-based VLANs are. What it means is every PC, every device yaya kuno attach to this interface, automatically iri kupinzwa VLAN 10. Why? Because every time traffic painosvika painterface apo paswitch redu apo ndo pariiswa tag yeVLAN 10. PC1 iyi tikaibvisa panapa tikatora PC2 iyi tikauya tikaipfekera apa inobva yapinda muVLAN 10. Excuse me. So interface-based VLANs, basically VLANs edu, they are fixed by the interfaces. We have MAC address-based assignments where VLAN yedu is based on MAC address of a device. So ndokwanisa kuya ndomepa MAC address yePC yangu iyi ndobva ndaisa muVLAN 10. What it means is MAC address is the one which is being mapped neVLAN. PC yangu iyi ndikaibvisa, PC yangu iyi ndikaibvisa ndikauya kunoisa imwe PC, MAC address neVLAN yangu will not match the map yandinenge ndaconfigure on my network. Zvirova kuti another PC won't be able to connect up. That is what MAC address based VLAN assignments look like. Unoita mapping yeMAC address yako neVLAN. So PC can change a device. If a device changes, then MAC address changes. That becomes a problem because your mapping will no longer match. IP subnet based assignments, those ones, they are facilitated by a device which is able to route. Layer 3 IP subnet based assignments. So we need my layer 3 devices, more specifically my layer 3 switches. For every subnet, we assign a VLAN. In this case, you can see kuti VLAN 10 yedu is being assigned to a specific subnet. Aya anowanzofambidzana aya. Interface based ne-IP subnet based assignments anowanzofambidzana, because for every network yatinayo VLAN 10, you're going to realize that the network ID of all my devices are on VLAN 10 will be different from the network ID VLANs devices are on VLAN 20. So the interface-based assignment in IP, subnet-based assignment, they're kind of similar, zvinodyidzana. Then we have protocol-based assignments. VLANs edu, they're based on specific protocols. So you could have a VLAN 10 belonging to traffic IP only, VLAN 20 belonging to traffic IPv6 only. That's that is a protocol based. The last one is more to do with policy. My security policies, for example, you could have my security policies where you implement different VLANs depending on the policy that a company has. But in this course, we focus on this one. Uh, ish, it's not as useful, it's not as flexible as well. It's usually um useful my devices which are not to be changed. My devices asingangochinjwe. It's not as flexible, this one, MAC address based. Then R2, my configurations are actually they're a bit complex. Are not gauche. So for this course, we'll focus mostly on interface based assignments. Very easy. Interface based VLAN assignments principles. A network administrator pre-configures a PVID for each interface and assigns each interface a VLAN corresponding to a PVID, a port VLAN ID. I think this stands for port VLAN ID. I think so. So with interface-based VLAN assignments, interface ready is assigned a PVID. That's basically what it's saying. An administrator manually configures an ID for the interface. So if I configure PVID yangu kuti 10 panapa, like I said before, every packet richafanana nepanapa, every frame richafanana nepanapa, rinobva rainserterwa tag rekuti it belongs to VLAN 10. After an interface receives an untagged frame, the switch adds a tag carrying the PVID of the interface. The frame is then transmitted in the specific VLAN port default VLAN ID. Okay, port VLAN ID, PVID. Default VLAN ID for an interface value ranges from 1 to 4094. Typical question. Range of my VLAN IDs, Edu. A VLAN ID can go from 1 to 4094. 1 being the default. This is the default PVID. All devices belong by default to VLAN 1. You cannot create, you cannot delete that one. Every other VLAN you can create, you can delete, you can remove them from the devices. So very important to know kuti VLANs edu haasi kuconfigure pa PC, ari kuconfigure pa switch. MAC addressed principles. VLANs are assigned based on source MAC addresses. Administrator pre-configures the mapping between the MAC address and VLANs. After receiving a tag frame, switch adds the tag mapping the source MAC of the frame to the frame. Mapping table records the mapping between MAC address and VLAN IDs. Okay. Layer 2 Ethernet interface types. The type of interfaces that we have an access interface. I think I discussed an access link. So an access interface is used to connect to a switch, connect a switch to a terminal such as a PC. In general, the NICs on such a terminal receive and send only untagged frames. An access interface can be added to only one VLAN. Runs access interface if reconnected to an end device. Runs an access interface. Rimwe interface iri reconnected to another switch. Runs a trunk. So iri reconnected to an end device. That's an access interface. Link iri ndorinozi access link. Link iri ndorinozi trunk link. Panapa panofamba multiple VLANs. Panapa panofamba only one VLAN. That's the difference between an access interface and a trunk interface. Then in a hybrid interface, a hybrid is a hybrid. It's a combination of an access or a trunk interface. So you could have an interface which behaves as an access or as a trunk, depending on the connections it's repo on that interface. That is what defines a hybrid interface. My access interfaces edu, how do they behave kana ka receiver traffic? This part is very important. Important understanding EPUB. A lot of questions are over EPUB, but my diagram is told. Right. In a case where we are receiving untagged and untagged frame, what happens? So kana ndine switch rangu, ndine PC yangu, we are saying pane traffic yauya paswitch, traffic iyo inouya iri untagged. In this case, kana ibva paPC, ndo scenario iri apa iyi. Traffic iri receivwa from a PC, if we can say an end device, traffic yedu is untagged. What happens to that traffic ikasvika paswitch, inside of the switch? Traffic yedu yasvika paswitch apo, what happens? So like I said, traffic yedu ikasvika paswitch ichibva ku-end device via the access interface, inosvika via pure tag. So the interface permits the frame and adds a VLAN tag carrying the PVID of the interface. Inopiwa tag yakaita sei, inopiwa tag with respect corresponding to the PVID of the interface. So interface redu iri tinoripa a PVID, port VLAN ID. In this case yapiwa VLAN 10. It means every time pana untagged traffic richingosvika apo rinobva rapiwa tag kuti ndere VLAN 10, and there we have traffic yedu yatagged. Inside a switch, taku receive a tagged frame. What happens if we are receiving a tagged frame? Scenario a tagged frame hatichabve paPC. You could have a scenario where pane frame uri kubva panapa richienda ukuku, rinogona kuva riri tagged. You cannot have a tagged frame richibva kuPC apa. But palink iri patrunk apa ndinokwanisa kubvisa tagged frame richibva kunoku roenda uku. Kana richisvika panapa, what happens to it? Ndo panapa patiri apa. So tagged frame redu rikasvika painterface panapa, which is the trunk interface in this case, what happens? If the VLAN ID of the frame is the same as the PVID of the interface permits the frame. If the VLAN ID of the frame is different from the PVID of the interface discards the frame. So if VLAN ID matches the PVID of interface ID, it basically means frame rate is accepted to the VLAN switch. Then it can be later be forwarded kwarinofana kuenda to the destination with respect to the VLAN riripo. If this value E tag E does not match PVID at all, then it's dropped. So in a case yekuti pane ngati kumboita VLAN 10 20 ish. Can I do this? VLAN 10. Can I do this? VLAN 20. So traffic yedu ikabva. Okay, this doesn't work. Let me not complicate things this early. How many minutes? 3 minutes. Right. So for this case, two scenarios. IDE ikamecha PVID panap. Good. If it doesn't match, traffic head is dropped. So if it matches inoperable switch, then it can be forwarded. If we are now sending my frames, if the VLAN ID of the frame is the same as the VLAN ID, PV ID of the interface removes the VLAN tag from the frame and then sends the frame outside. And then sends the frame to the destination. Right. From inside the switch, take the frame umo. Kana rakusendwa out in interface. If this tag matches ID panel, then it means we can remove tag information. To remove a tag, it's usually a PC on this other end or an end device. If it does not match, it is dropped. So we have my scenarios in summary. We have my scenarios. Can I find this? No. We have my scenarios, two scenarios. Let me see. We'll create a blank page. See what lines. Screen, blank screen. Right. We have my scenarios. So this is PC1. This is PC2. So PC1 is in VLAN 10, or let me put it this way. Interface E, it's VLAN 10. Interface E, it's VLAN 20. Let's have another interface here, PC3. Let's say it's 20. No, let's say it's 10. Less than 1 minute. Will I be able to finish? Right. So traffic yedu ikabva from this PC ichida kuenda ku PC number 3. What happens? Yeah, I don't think my time will be enough. Let me just start this one after I start another session. Join using the same link.